Ever wondered how your phone predicts your next word, or how self-driving cars react to sudden obstacles? The answer lies in online algorithms, systems that learn from data in real time, one piece at a time. But here's the challenge. These algorithms can't revisit past decisions. They're like chefs who taste a dish only once, never revisiting the recipe. The question is, how do they know if they're right? Let's break it down. Traditional machine learning tools, like confidence intervals, rely on seeing all data up front. Imagine baking a cake and only tasting it after it's done. How would you know if the recipe needs tweaking? Online algorithms, like stochastic gradient descent, (SGD), adjust step by step, using each new data point to improve. But without a full view of the data, how do we measure uncertainty, that critical error margin that tells us how confident we should be in their results? Enter HulC, a breakthrough in online learning. Think of it as a statistical shortcut. Instead of calculating a tricky value called asymptotic variance, which requires reprocessing all data, HulC uses the algorithm's own outputs to build confidence intervals. It's like the chef tasting the dish after each step, not just the final product. This makes HulC computationally efficient. It doesn't slow down the learning process, and asymptotically valid, meaning it gets more accurate as more data arrives. What sets HulC apart? It works even when the algorithm's inner workings are complex. For example, when using Polyacc averaging, a technique that smooths out SGD's noisy updates, HulC still delivers reliable confidence intervals. Researchers tested it on real-world problems like linear and logistic regression, and it outperformed older methods that either lagged in speed or needed extra memory. But here's the catch, even the best tools have limits. The paper shows that SGD's performance can be super sensitive to tuning parameters, like the learning rate. Small changes can lead to big differences, making it tricky to trust results without proper checks. HulC isn't a magic fix, but it's a major leap forward for making online learning both fast and reliable. So next time you see AI making split-second decisions, remember, statisticians are solving puzzles like these behind the scenes. HulC is a reminder that innovation isn't just about speed, it's about understanding the limits of what we build. Thanks for watching and stay curious. Ever wonder how scientists and AI systems know how sure they are about their predictions? Like when a model says this email is spam, how do we know it's not just guessing? The answer lies in confidence intervals, and today we're breaking down a study that's rethinking how we calculate them, especially with massive, messy data. Imagine estimating something tricky, like the average height of 1 million people. You can't measure everyone, so you take a sample. But how do you know your guess is good? Confidence intervals are like a net that catches the true average. The narrower the net, the more precise your guess. But here's the catch. If it's too narrow, you might miss the real value entirely. The study compares 3 methods for building these nets: ASGD plugin, HulC, and tstat, against a classic called the Wald method. The goal? To find the perfect balance between precision, narrow intervals, and reliability, coverage, how often the net actually catches the true value. Here's the key insight. The ideal interval has a width ratio of 1, meaning it's as tight as the Wald method. But in reality, some methods go overboard. The ASGD plugin, for example, makes super narrow intervals, but at a cost. It undercovers, meaning it misses the true value more often. Meanwhile, HulC and tstat create slightly wider nets, but they're way more reliable. Now here's the twist. The performance of these methods depends on 2 things: sample size, how much data you have, and a hyperparameter called C. Think of C as a tuning knob. Set it too high, and your net blows up in width. Set it just right, and you're golden. In low-dimensional settings, like estimating just 5 parameters, C around 0.5 works great. But in high dimensions, say 100 parameters, things get wild. You might need thousands of data points just to get a stable interval, and the sweet spot for C shrinks to a hairpin. And here's a kicker. The Wald method, our baseline, isn't always reliable. In high-dimensional scenarios with small samples, the data can be ill-conditioned, like trying to solve a puzzle with missing pieces. In those cases, the Wald interval can't even be computed. That's why researchers are pushing alternatives like HulC and tstat. So why does this matter? In real-world applications, like medical diagnostics or financial forecasting, getting the balance right between precision and reliability can mean the difference between a life-saving insight and a costly mistake. And as data grows more complex, these methods are our best bet for staying grounded in uncertainty. Next time you see a model make a prediction, remember, behind the scenes, scientists are fine-tuning these confidence intervals to keep the chaos in check. And that's the science making AI smarter, one net at a time.